Oh, come on, I can't get another one. It wasn't my fault, I swear. Please, you're cleaning the room is already a mess. What could possibly break this statue except you? Entropy. What? Entropy, the thing that made this statue to change from one form to another. Boy, that's not true. Do you even know what entropy means? Well, I know one or two things. I know the entropy is the study of disorder in our universe, and according to the entropy laws, the complexity of the universe is decreasing. So naturally, this statue will turn into fundamental particles anyway. Dude, you've completely destroyed the meaning of entropy. Entropy does not talk about the particles, and it is more complicated than that. But hey, don't worry. We'll talk about it. Yeah, someday we'll talk about it, not today. Hey! We'll talk about it now. In this great and vast universe, energy is transferred between objects in different scales or changes from one form to another. Energy could be anything. It could be electricity, plasma, heat, temperature, nuclear fusion, and sometimes even mass. Usually, the energy is described as heat, which seems logical. Because if you take a good look around you, you'll see that almost everything in our daily life is working on heat. Heat travels through the cosmos as radiation, which is a wave of energy that is transferred from hot to cold bodies. This diversity in the energy mechanism, which can cause the formation of different particles, can also cause the destruction of the whole atom infrastructure, which they will eventually transform into fundamental particles. These processes are not disturbing or unusual. In fact, all the evolutions and transformations that happen in the universe begin with these steps. But the universe will not stay like this forever, and it will definitely change in the future. There are many theories agree that the universe will lose a large part of its heat in the future. This is known as the heat death. The temperature of the entire universe will be an infinite fraction above absolute zero, which just right at the temperature with no more energy will be extracted from an atom. Also, if the universe expansion velocity in the future will be greater than now, the empty space will be so much expanded that the particles will no longer have the enough force to hold each other. But here comes a question. Do we have to blame the expansion for all these events? Is there a force that causes the bodies to turn into fundamental particles and break down to it? What law governs the changes in our universe? Well, we'll talk about it now. Whoa, wait, why are you doing it twice? Do what? The video entry, you did it once. I did? Yeah. Why am I paying you? Now, let's see what the general meaning of entropy is. The simplest definition is that entropy is the unit of measuring energy disorder in a set or a collection of particles. But don't stop the video from here and claim that you know what entropy is using only this definition. Entropy is a really complicated topic, and it's okay if you didn't understand it after watching this video. It took me even a few days to understand it. Man, I can't have shit in this house. But to reduce confusion, you should know that in entropy studies, we only talk about heat and energy. It may sometimes talk about the matter because the matter itself is made from energy. No matter how chaotic this beautiful universe seems, in atomic scale, a certain order can be observed. In other languages, this order is not the only meaning for entropy. In Greek, entropy means transformation or turning. But This meaning is almost describing the entropy definition. Entropy has many different meanings depending on what matter you are studying, but in general meaning, it is the study of energy disorder. Well, let's take a simple example. I have two glasses here, one filled with ice and the other filled with water. Which one of these two glasses has more entropy? At first glance, you might think that the one with ice has more entropy, but the answer is not correct. I know, at first you thought that the glass of ice has more entropy because it is melting with the temperature of this room, so basically it is changing more. But you should be reminded that ice as a solid has more stable shape than water as a liquid. Because when we are studying entropy in two bodies, we are actually examining their energy, and we can understand it better when we are zooming. The molecules of these ices are connected by these bonds, which they'll need energy for it. Just a small reminder, gluon, the particle that connects the quarks of the proton and neutron, has nothing to do with these bonds, and we are actually talking about the molecules. When this bonding molecule meets another molecule, they may sometimes have unequal energy. Maybe one of them has more energy and maybe the other one has less. And this is where entropy intervenes. Entropy defines the difference in energy between these two bonds. For example, if I put some ice in this cup of tea, it will become iced tea. Hot tea and cold ice actually have energy difference or entropy between them. After a while, the ice melts in the boiling tea and the tea cools down. The energy now is equally divided between the two, and the temperature of the glass is now moderated. Now you know why water has more entropy than ice. Water molecules are swimming and jiggling, which consumes a lot of energy. On the other side, the ice, whose molecules are stable and have a stronger bond, and the energy between them is not being transferred. But remember something, when we are talking about entropy, we don't talk about the individual molecule itself, but we are talking about the collection of molecules, like the glass of water. I pour water in the other glass. We never see the reverse unless I'm a wizard or something. But if we enter the world of molecules and reverse the process, we will not see a big change. So we can determine the entropy of an object through the collection of particles.
Hey man, wait.
Yes? Well, now I'm able to recognize the entropy between two objects. And we know in every object there is some amount of static energy. But does the body alone have an entropy? Well, let's imagine that we have a stone on a hill. The static energy in this stone remains until a movement occurs and sets it in motion. For example, throwing it from the hill. At the same height from which the stone fell, more energy was spread and more entropy and disorder can be observed. In fact, the entropy of a particular object can be easily recognized, and there is no need for another object to transfer energy. In order to make it easier for the scientists to give examples about disorder, they use the organized room analogy. Let's say you entered an organized room of a teenage boy, which is impossible, but it doesn't matter. In this room, you can look for things and find them more easily, because you can look things better when they are in order. So it has less entropy. Now, let's say that the room is a hurricane and everything is scattered. For example, if we were looking for a book, it would take more time to find that book. So this room has more entropy. But think about it. If the room is a mess, but the owner can find the stuff easily, like even though it's a mess, they know where is the mess and they find their stuff, then it is known as organized chaos. So the next time you're cleaning your room, you're not listening to your mom. You're obeying the laws of physics. In 1850, German scientist Rudolf Clausius created the concept of thermodynamic system. After years of research, he expanded his theories and made up the term entropy. In fact, in the second law of thermodynamics, the word entropy was directly mentioned for the first time. The second law of thermodynamics states that by transferring or converting energy, more of it is wasted. It is one of the four laws of thermodynamics that describes the relationship between thermal energy or heat and other forms of energy and how energy affects matter. Today, after these explanations, you can tell that you understood the entropy topic. But as I said, it's a really complicated topic and we'll need a lot of videos to explain it more broadly. Science is always difficult, but never impossible. Okay, enough flattery. Look, I have a question. I think we better end. Okay, yeah, one question. You gave an example about the time reverse and entropy, and you said that depending on the object, it could change its possibilities. Does that mean that entropy can intervene in statistics and probabilities? Of course. But we'll leave this topic for another day. Until that day, do not stop wondering and be curious.